Hello, I'm Tom Chastain, Milling Product Manager with Wirtgen America. Today we're going to talk about milling for smoothness and quantities. Now, no matter what size a milling machine is, it could be 14 inches wide, 14 feet wide. You strip it down, that's what we're looking at. A milling machine's made for the controlled removal of asphalt, yes, sometimes concrete, sometimes dirt, even cut salt with a milling machine. But why do we use milling machines? Real simple. We have roads that look like this. We're trying to make them look like this. If you think about it in an artist standpoint, the job of a milling crew is to give the paving crew a clean palette to paint a masterpiece on. If we mill it correctly, the paver theoretically should be able to sit on the joint, nail out the screed, give it half a crank, and never look back. Does it work that way? Not very often. With every milling machine, this is the lifeblood of the machine, the cutter drum. If the drum is not in proper working order, we're not going to get our quality, we're not going to get our quantities. So some things we need to check. Obviously, we need to check the milling teeth and the holders. Make sure they're in proper working condition. Kicker paddles. Most milling drums have kicker paddles there to assist get the material out of the cutter housing and onto the conveyor. We need to check our wear items, such as the rear moldboard, rear scraper, wear plates. The side plates or the end gates of the milling machine as well, make sure those are in proper working order. If, say, your rear scrapers are worn out, more than likely we're going to leave a lot more material behind the machine. That's going to increase our cleanup time as well. Make sure you have spare cutting teeth and holders. Get on some of these projects, maybe it's a little different asphalt, maybe there's some hidden treasures under there, but we're going to need some spare teeth and holders, that way we can maintain that quality in the drum. Need to make sure we check our spray system as well. I will talk about water in a little bit, but we need to make sure that that water spray system, especially to the drum, is in proper working order. Now when it comes to grade controls, there's a wide array of grade controls out there. From smart cylinders, wire ropes, slope, pause at slope. We need to have an understanding if we're trying to mill at a particular slope. Depending on road conditions, you may get daylight, you may get dirt. The machine's going to give you whatever percentage you set it at. So if you're out there with a smart level, calibrate the smart level to the machine. You can put the machine at 0% slope. That way, you and the machine are on the same page. Moving on to ultrasonic sensors, sonic 5-eyes for string line, rotary, laser, and 3D. 3D's come on strong here lately for a lot of various projects. Big question we need to ask ourselves. Are we copying or profiling the road? There's a massive difference between the two. When we copy the road, basically we're referencing off our side plates. What we see is what we get. And if we don't have we have a less experienced milling crew, if there's a bump in the road, there's going to be a bump in the road once we mill over it. Now, here's another thing. If we're milling at a higher feet per minute, hydraulics on the machine need time to react. And if you're milling really fast, not only is that bump going to be there, but you may actually elongate that bump because the machine's trying to react to it. So it's actually very counterproductive. So when we copy the road, we mill it, we pave it, you look behind the paver, it looks really good. Until you put the breakdown roller on it, we're exactly back to where we started. That's copying the road. This animation shows the same thing. Machine's going down the road, it comes across a bump in the road, the side plate sense it, the machine reacts, we still have that bump in the road. Now profiling. Profiling means we're running like an averaging system. Somewhat like what you see on a paver, but they're laying it down, we're picking it up. So with an averaging system, you're averaging over the length of the machine. So instead of having that one big bump, now you may have 3 subtle bumps depending on the road conditions. I use this analogy all the time. It's like having a ball of Play-Doh. You flatten it out. Is it flat? No, but it's a lot flatter than it used to be. Depending on the road, you may have to cut it 2 or 3 times to actually get it perfectly flat. But utilizing a sonic system does give us a higher quality ride. This picture just shows kind of how it's set up. You can see the sonics in blue, front and back of the machine, and the side plates are in the red. So that side plate, because we're running smart cylinders, acts like a contact averaging ski as well. Now here's that same bump in the road. Now we're profile milling. So you see the sonic picks it up. There's the first one, side plate gets it, and then our third sonic. So it gives us a much smoother ride. Now, starting off. My philosophy when it comes to starting off is start slow, stop slow. Here's the reason why. Got the machine zeroed out, we're ready to go. We engage the drum, set our depths, put the machine in the cut. Remember what I said, hydraulics need time to react. Start the machine off slow until the tracks get into the cut, especially if you're running a center mounted machine. So once the tracks get into the cut, we can ramp up our speed from there accordingly. If we just come barreling off the joint, the machine hasn't reacted, immediately we put a dip in the road. Now, slowing down, we don't need to go from 100 feet per minute to 0, because that causes problems as well. We get things that look like this. We don't really want to see that, and most areas don't. You see the drastic change in the pattern quality from going from fast to slow. Now this is basically showing what we call a standard space or 5/8 space drum. In this animation, the red teeth are going to hit red, green, green, yellow, and yellow. But why do I show you this? Based on your feet per minute and drum speeds, the slower you go feet per minute wise, the more hits in a shorter distance those teeth are going to make, tighter the pattern, smaller the wrap sizing, hopefully. The faster feet per minute we go, the more of a dragging effect we have, the more coarse the pattern, larger the wrap sizing could be. So there's a lot of variables we need to look at. Okay, what is our tool spacing as far as our line spacing on our drum? Also, which cutting tools we're using, large carbide, small carbide. There's a billion questions. Our milling speed, are we milling high speed or low speed? And also our milling drum speeds. Most of these new machines coming out have variable or different settings for drum speeds themselves. Now both of these are exactly the same line spacing drum. The machine on the left is milling faster than the machine on the right. Does it change its line spacing? No. What it does change is our pattern quality and our wrap sizing. So here's a side view that you can see the one on the left and the swipes that it's taking. Not only is it making a poor quality pattern or what we leave behind, we're also burning more fuel and we're cutting the life cycle of our cutting tools down drastically. Now the way it used to be when we stop in between trucks, the machine would take off again, we would see that little dip in the road. A lot of people thought it was a machine settling. It's not. When you're milling and you're going forward, you have pressure on the cutting tool or the tooth that's holding it tight to the holder. When you stop, that pressure is gone and the tooth actually relaxes 1/4 of an inch. So you get what you see there on the right. You get that little indentation. Now with new machines, what happens when the machine stops, it actually picks itself up that 1/4 of an inch, so we don't get that divot in the road anymore. Now it used to be if we wanted to change our milling operational option, we were changing drum shifts. Now we can do it with the push of a button. So 3 big ones, we have eco, power, and performance. So eco, say we're doing complete removal of asphalt getting in the dirt. We can run in eco mode. That's going to basically, it's still torque. We're still getting all the torque we need to the drum, but we're saving on cutting tool and fuel consumption. Power, that's exactly what it means. We're looking for like thin to medium depth asphalt, and we're trying to get the most out of that machine as we can. Performance or pattern mode, we're more looking towards the profiling aspect of the milling machine. So now what we can do, where it used to be when you stop the machine where you were milling and you hit a hard section of asphalt, the machine would slow down just because of force. But the drum would still be trying to turn at the same RPM, thus our pattern would change. With these new machines, you could go in, tell a machine what drum you have, what teeth you're running, and what pattern you want that machine to maintain. So now when we're milling and we come across that same section of asphalt, you can see the difference between the right and the left. The right side will be the old way. You look at the left side, see how the drum actually slows itself down. That's all done electronically. The operator doesn't have to do anything about that. That helps us try to get that higher quality. Now this is based upon the fact we've done drum maintenance and everything's good. At 100 feet per minute with a standard space drum, that's what the pattern looks like. So you can do a cutout and actually see your peaks and valleys and where those teeth are hitting and where they're not. So that gives us a higher quality as far as we have an understanding as far as what our drum is actually doing. Now, we'll talk about feet per minute. Now, when it comes to milling, anyone who's been around it, a lot of times we like to go fast. Okay, we're production-oriented kind of people. Therefore, when you give us the green light to go, and then you say something like, we have asphalt on its way, you just lit a very short fuse. That could get us into trouble. So all these pictures I'm showing you now, based once again on the fact you've done your drum maintenance. At 30 feet per minute, that is a tight pattern. That's almost like straight line milling. Minus the line spacing, it almost looks like a fine texture drum, but it's not. At 60 feet per minute, you can see how that drum's designed to auger that material towards the center. Still a good pattern. Now we get over 85, 90 feet per minute. Okay, now we have an issue. We're starting to get a little bit more coarse of a pattern, starting to get a little bit rougher, and that wrap sizing starting to get a little bit bigger as well. You get over 170 feet per minute, now you're chevroning. You're actually outrunning the cut. The machine's walking faster than the drum is actually turning. So here's some examples of what not to do. There is 210 feet per minute. You can look behind the machine and see the skips in the road, the chevroning. Crazy thing about this project, we only had 5 trucks and they were not paving the road back that day. The road's a little famous. It's called Interstate 75. There's 240 feet per minute. 3 trucks not paving it back that day. You can see the chevroning behind that machine as well. There's 260 feet per minute. They were not paving it back that day. And funny story about that video, right around the corner up there, they hit a buried manhole cover at 260 feet per minute, causing a little bit of damage to the machine. There's 303 feet per minute. Okay, remember I said milling, we're kind of production oriented. You're not going to put us in a race car and expect us to go 30. Okay, there are trade-offs to it. So when you're milling at speeds like that, you're not milling, you're excavating. You're ripping material out of the ground. So because we have such a high utilization of wrap material currently, and maybe we were going to screen it, but now we got to crush and screen it so we can utilize that wrap. We've added a process to maybe we hadn't thought about. That's time, that's money. So trade-offs at milling at high speed. You're not actually cutting the depth you set. The machine just can't keep up. Because the force is working against the machine's actually wanting to water ski. It's trying to find that path of least resistance. So we're going to have some highs and lows. Our poor pattern now means we've lessened the interlocking capability of the pavement to the milled surface. Simply, we're making one half of Velcro. The paver's making the other half of Velcro. Due to our erratic depth, now our asphalt tonnage is off. As we all know, asphalt's not cheap and it's not going to get any cheaper anytime soon. Our compaction numbers are going to fluctuate. We always preach about continuous paving, continuous rolling patterns. Maybe we set a certain VPM and frequency on the breakdown roller, but because our millings and we have those highs and lows, maybe it was a thin lift mill and fill. Now that breakdown roller comes over it, we break aggregate. It's not the paver's fault, it's not the roller's fault. It's the milling machine's fault. Doing milling that fast, you're putting an unneeded amount of wear on the machine. Milling machines are already beating themselves to death. When you push them to that ragged edge, you're just lessening the life of that machine. You're just beating it up that much quicker. Once again, sizing material. We want to utilize that wrap material and get as much quick turnaround as we can on it. All that equals low quality, wasted material, and loss of money. No one wants to hear loss of money. So there's a wide array of different drums out there. So some people think that, okay, well, standard drum, my pattern doesn't look that great. So maybe I should put a fine texture or micro drum underneath my machine to get that higher quality, plus allow me to mill at a higher feet per minute. There's trade-offs, so we have to have an understanding of these drums. We'll take the big three. Standard drum is made to mill the machine's maximum cutting depth. If that machine is capable of cutting 14 inches deep, that drum is the one that can do it. Now, fine texture and micro. Notice they both say thin lift or profiling. Why do we have two different drums that do the exact same thing? Every state varies. Different projects, as far as what we're looking for smoothness-wise out of that. Now the thing is, you don't want to cut deep with a fine texture micro, because if you look at the drum on the top, in between those wraps of teeth, that's called space. That's for material flow. If you look at the fine texture micro drum, what you don't have much of is space. We just can't get the material out of the housing. That's why you're limited on your cutting depth. So once again, our standard drums, maximum cutting depth. Fine and micro, thin lift, or profiling. Now here's some patterns. This is a standard pattern. It looks good. That's a fine texture pattern. And that's a micro pattern. Here's what we need to understand about fine and micro. If we're going to try to utilize this wrap material in our new mixes, when you hit the ground with that many teeth, you're going to lose 10 to 15% of that wrap material. Reason being is you've hit it with so many teeth, you've turned aggregate into dust. So we're going to lose some of that just because of that. Now, here's some utilization that you can use fine and micro for. So maybe we have no grip on the road. We could do it the old way, where we come in and mill it off a few inches, transport it away, bring the asphalt back, pave it back. Big process. If you use a fine or micro drum, you could come in, fine texture mill it, carry the material away, and you're good. Maybe we've got, some wheel rutting issues. Same thing. Mill and fill, fine mill it, transport that material out of there. We're saving on cost. Maybe our profile wasn't true. Same thing again. We could mill off the complete surface to get it back on profile, or we could come in, fine texture mill it, and just carry that material away. There's a lot of savings and a lot of utilization we can get out of these drums, just besides getting a smooth pattern to pave over it. Now, the one negative trade-off when it comes to fine and micro drums, somebody's got to change all those teeth. On that drum right there, you see that's about 1,000 teeth. And you can tell by his face, he's not very happy. Now let's talk about teeth for a minute. Milling teeth, when they engage the ground, they can generate upwards of 1,800 degrees Fahrenheit. You don't know what that is? That's called hot. Extremely hot. So you take that heat and the abrasiveness of the material that you're cutting, that's actually where we start to get tooth wear. That's where that carbide tip on that tool starts to break down. That constant heat and the abrasiveness starts to wear and tear and just slowly break the carbide down. So when it comes to milling, Water is your friend. Okay? Not only is a cutting tool coolant, it's also a lubricant. We're trying to keep those teeth rotating as long as we can to get good wear on those cutting tools. Obviously, it's a big thing with silicate dust. We want that dust suppression. Okay? Yes, we do utilize surfactants sometimes on these projects, soap, which do come in handy. The reason I like running soap and water tanks, not only does it trap more of that silicate dust, but you take some of these high polymer mix designs, and those fines want to stick to the machine throughout the course of the day. But when you wash the machine at the end of the day with soapy water, it's almost like spraying the machine down with cooking spray. Those fines don't want to stick as much, which is a good thing. So that soapy water also helps prevent buildups of components. You get a lot of buildup, say, on the head pulley of the conveyor. Now the conveyor doesn't want to track right. We can actually start to delaminate the belt from the inside. We lose a belt, we're down. Let's go back to cutting tools. When a tooth is in the ground and it's engaged, some people think the tooth rotates while it's engaged. It's not. It's actually flexed. There's forces working against that tool, kind of pressing that tooth back. Where the tooth rotates is once it releases from the cut. We get that kind of boomerang action, it flicks off, and then the tooth rotates. Between that material flying around and vibration, that's where we're getting that cutting tool movement. Now there's a billion different kinds of milling teeth, okay, for hard asphalt and soft asphalt. So you take this animation here. Hard asphalt, more prone to wear the carbide tip down sooner. Soft asphalt, because it's almost like sandy, is going to want it to wash the body of the tooth out. Okay, some may think that one's better than the other. If it's soft asphalt, you may wear the body down so far that the cutting tool tip, the carbide tip, actually snaps off. Still a bad thing. We try to find the tooth that best suits our applications. Now you look at this picture here. What we want to see is what we see on the bottom. What we tend to get is what we see up top. It turns into a hodgepodge. We'll have old holders, used teeth, new holders, old teeth. It gets our pattern out of tune. We want to maintain a quality pattern. Now if you look here, real simple, how we spot bad teeth. There's one, there's one, there's one, there's one. I could actually gone all the way across this picture and shown you that. How the machine shows us we have a bad tooth is we start getting a white streak behind the machine. That tells us as a cutting tool is locked up. It's no longer rotating. It's flat spotted. That's what a flat spotted tooth looks like. Now, if we don't change that tooth, what happens is all of a sudden we get into the holder, whether it be bolt-on or tapered fit. Now, these drums are designed, most of these drums are designed to hit 36 degrees angle of attack, 5 degrees askew, give or take. Now, what some people do, they get into the holder and say, hey, just put a new tooth in, we'll be okay. You're not. Because you see on the right, we've changed the angle of attack that tooth engages the ground. That tooth on the right will wear out 3 to 4 times quicker than normal. Reason is, it's not hitting the carbide. It's bouncing off the steel body. You'll notice it behind the machine in the pattern because it looks like a crescent moon or a scuff mark. What we need to do is address the holder situation and get it back on plane. Now, if you continue to run with a bad holder, you see there, sometimes you get that. You've gone from cutting asphalt to bludgeoning asphalt. What you see on the left is like trying to cut asphalt with a Baskin-Robbins tasting spoon. It's not going to work well. The machine's going to let you know. It's going to be very abusive. It leaves you with something that looks like that. That drives your cost of operation up, and it kills your quality. The only people who want to pave over that is the milling crew that did that. So in conclusion, have we maintained our machine? We have better chance to achieve our quality. 30 minutes at the end of the day will save you a lifetime of headaches. If we try slowing our feet per minute down, we have a better chance to achieve quality. Standard milling job, you're only milling half an hour out of an hour usually, depending on your trucking. Instead of running at 120 feet per minute, try running at 85, 90 feet a minute. Look behind the machine. You'll see your pattern quality and the wrap sizing improve. Communication with our team. You got to have that open line of communication. That way everybody knows who's on the project, what we're expecting, and what we need to do. All of that, but you got to put safety first. In road construction, as we all know, there's been a lot of horrific things happen throughout the course of the years. We got to put a protective bubble around not only the milling machine, but that entire project. I'm Tom Chastain, and I thank you so much.